This is a presentation of a heat exchanger's dynamics and controls utilizing Simulink for the 2018 Simulink Student Challenge. First, let us look at our double pipe heat exchanger problem. Our problem is to model, design, and develop a double pipe heat exchanger and proportional interval or PI controls in Simulink. For this, we are also utilizing MATLAB. Before we begin our calculations, we must start with some initial system setup. For system setup, we note some key equations and assumptions. A few of these notes are listed below. Moving into Simulink in MATLAB, we have our model creation and analysis. This begins with our MATLAB calculations. Utilizing the tool of MATLAB, we are able to perform our calculations for our initial setup of our simulation system. Here we have our command window where we perform all of our calculations. We have our editor window where we are able to keep track and save all of our commands. And we have our workspace window where we save all of our variables that we have defined. For our system, we defined all of our state space variables. We defined our state space model and calculated it, and we derived our transfer functions so that we may use them within our Simulink simulation model. We begin with our Simulink initial system setup or open loop setup for a heat exchanger. As shown, we have our hot side fluid flow simulation and our cold side fluid flow simulation. And while these overlap for the transfer functions to give us our output responses. Our input responses for the system are the hot side and cold side inlet temperatures, and what we desire for our output is to know how our output behaviors respond. Moving into our final system, or our closed-loop system, we were able to implement our PI controllers for our heat exchanger. Through here, we are able to look at how the system behaves for the output responses or outlet temperatures utilizing these controllers. Some key functions for Simulink is its user-friendly ability. For an engineer, it's important to be able to change values and run multiple simulations, and Simulink allows this. For example, we have our pop-up window for our block parameters for the step function for the hot side. Here, we are able to quickly change any of the values that we would like to redo our simulation. Through our simulation runs, we are also able to get our output scope number 5, which is our hot side flow output response and our cold side flow output response. And we are able to easily and quickly see how the system behaves. Some of the key system responses. For the controller's response, we will look at a few comparisons, and we'll look at how the PI controllers controlled the system. We have the hot side output responses, as well as the cold side output responses. For this, we will look at one of these charts. Utilizing the controls, it's shown that we have a faster settling time with very minimum overshoot and very minimum steady state error. And you can see, utilizing our controls, that our system actually performs better and quicker than if we just let the system handle naturally. We are also able to look at how our system controls as a whole. By utilizing these two graphs, we are able to see how our output responses respond to the input responses we used for the controls. The importance and applications of Simulink and the controls are as noted, as results show below. The addition of the PI control improves the dynamics of the system. Thankfully, using Simulink, we are able to run multiple simulations, and we are also able to tune these controls for optimum performance. This is additionally how engineers may be able to control or analyze systems to obtain their optimum performance. This presentation was created by our project team with our acknowledgement of the University of Texas at Tyler and our professor, Dr. Biswas.